Here we go. Heavenly Father, we thank you for this day. Thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. All right, so we are in Thumb and Foot, obviously. Section, I think we're officially in section, come on, stupid, 13.2, I think. Yep. And so the topic is algebraic extensions. So let's start with the definition of that. What is an algebraic extension? Definition: the element alpha in K is algebraic over F if alpha is a root of some non-zero f of x in polynomials over F. If alpha is not algebraic, over F, in other words, there does not exist any such k or polynomial, right? Then alpha is transcendental over F. Furthermore, the extension K over F is algebraic if each element of K is algebraic over F. All right? Let me give you an example without proof, okay? Just to get us going here. Some examples. Again, I will not prove, but square root of 2 is algebraic over, well, Q. And you could look at f of x equal to what? Over Q, we could look at x squared minus 2, yeah? Over R, we could just look at f of x equal to x minus root 2, yeah? Let's see here. On the other hand, pi is algebraic over R, since we can look at f of x equals to what? X minus pi, right? But pi is transcendental over the rational numbers. In other words, there does not exist, f of x in polynomials with rational coefficients such that f of pi equal to 0. Okay, some examples. So the, whether or not a number is transcendental or algebraic very much depends on context, right? What's the base field in consideration? Proposition 9 says the following: let alpha be algebraic over F, then there exists unique monic irreducible polynomial, which we will denote m sub alpha comma f of x in f of x, all right, for which m alpha f of alpha equals to 0. Moreover, f of x, a polynomial over f, has f of alpha equals to 0 if and only if m sub alpha f of x divides f of x. So how do you prove this? Let's see here. So we're supposing alpha is algebraic over f, right? What's that mean? What is it?
Transcendental over Q, that's supposed to be their denominators, right?
I figure I got at least a minute to spend with that question. Let's see here. Okay, so proposition 9, which essentially in words says that there exists a minimal polynomial for alpha. So if alpha is algebraic over f, that means that there is some polynomial which takes it as a root, right? So then just let m alpha f of x be the monic polynomial of least degree for which, you know, m alpha f of alpha equals to 0, right? I mean, the set of polynomials which take alpha as a 0 is non-empty, so we can apply the well-ordering principle because we're assuming alpha is algebraic, which means that that set of polynomials has polynomials in it. So let the well-ordering principle pick the degree, the smallest degree for which there is a polynomial taking it as 0. Without loss of generality, we can make it monic, right? Because we can just rescale the leading coefficient to 1. We're working in a field. And then the rest of the proof in Dumb-and-Foot basically is what? I mean, so suppose it was reducible, right? If m alpha f of x was equal to, say, you know, p of x q of x, that's not the son of a gun. That's not it. Let's see here. Oh, yeah. Suppose for p of x, q of x in f of x, right? He says, suppose that, you know, suppose you could factor it into, he's got a of x, b of x, with a of x and b of x both of smaller degree than g of x, all right? So suppose where what would that mean? He had the good sense in the proof to call this g rather than m sub comma alpha, I mean, my notation is horrible. I could just be writing g of x everywhere. I'm writing this instead. Anyway, so plug in alpha, what happens, right? I mean, that's equal to 0. Why? Because we're assuming that M is so constructed. But then what does that say about P of alpha and Q of alpha? One of them's got to be 0, right? We're in a field. There's no 0 divisors. So that implies P of alpha equals to 0, or Q of alpha equal to 0, which contradicts the construction of M sub alpha of f, right? Because it was the polynomial of least degree, which takes alpha as a 0. Consequently, what? Consequently, M alpha is irreducible, right? And the rest of the proposition follows from very similar arguments, right? So we can define the minimal polynomial in this way. Here's a corollary 10. Corollary 10, if L over F is an extension of fields and alpha is algebraic over both F and L, then M alpha L of x divides, divides what? M alpha F of x in Lx. He said this is immediate from second statement in proposition 9 applied to L. Since M alpha comma F of x is a polynomial in L of x having alpha as a root. Let's see here. Let's see if we can appreciate this with an example maybe. Can you guys give me an example where this corollary 10 would be meaningfully seen? Okay. So you want to look at... Okay, so you're going to take L equal to the reals and F equal to the rationals. And you want to look at alpha equal to, what was it? Square root of 2. So we have M alpha R of x equal to x minus the square root of 2. And we have M alpha Q of x equal to x squared minus 2. So M alpha R of x divides M alpha Q of x. In where? Right, because this is x minus root 2, x plus root 2. So where the division is happening is in the real polynomials with real coefficients. So this corollary 10 makes a lot of sense when you can just see an example. So definition. The polynomial M alpha F of x, or just M alpha of x when F is clear from context, is the minimal polynomial for alpha over F. Right. And the degree of M alpha F of x is the degree of alpha over F. So we define the degree of a number according to the degree of the minimal polynomial, which possesses that number as a root. Okay? And then combining what we've been talking about the last couple days with what we're doing right now, I mean, we can bring things together here with Proposition 11. Proposition 11 says the following: if alpha is algebraic over F and F adjoin alpha is field generated by, alpha over F, then F adjoin alpha is isomorphic to F of X mod parentheses M sub alpha of X. Or, as you guys prefer, wrangle M sub alpha X. Langle. I said Langle. I said wrangle. I should have said Langle. See? I'm out of practice if I didn't. You guys are funny. So, in particular, the degree of the extension of F by alpha over F is equal to the degree of the minimal polynomial of alpha over X, which is equal to the degree of alpha. And again, this is assuming that both of these are assuming that the base field F is fixed and understood from context. Somebody tells you that pi is transcendental. What's their context? Rational numbers, right? Those are number theorists who always work with the base field of the rational numbers, except when they don't. Seems safe to say, right? Okay, so moving along here. Moving along. So there was one example here. I mean, some of these examples we've already talked about previously, but I will mention them again ever so briefly. If alpha equals the square root of 2, then the minimal polynomial of degree 2 over the rationals, of course, is x squared minus 2. And so if we look at Q adjoin the square root of 2 over the rationals, that's a degree 2 extension. What's the question?
I was just saying that is not intuitive to me at all. I was just saying, that was just interesting to me, to prop 11.
Oh, yeah.
Just that those are connected in that way.
Mm-hmm.
I don't really have anything to contribute.
Oh, okay. That's fine.
Surprised.
Yeah. I mean, we were talking about this before, like R adjoin I, right, is R of X mod the minimal polynomial for I over the reals is x squared plus 1, So we looked at that one in some depth, but that's an example of this. Anyway. Okay, so if we take the rationals adjoin root 2, we get a degree 2 extension, and the minimal polynomial for root 2. Okay, great. Nothing surprising there. I wanted to mention here, if we look at zeta, an element of 2 to the 1 over n. So what this means is that zeta to the n is equal to 2. All right, so there are, as I talked about last class, n solutions to this, right? One of those always being the principal nth root, the real, right? For example, zeta equal to the just ordinary garden variety nth root of 2. That's one choice, right? But there are others, generally speaking. And what Dummett and Foote says here is that he's going to use the notation nth root of 2 to denote both the positive nth root, as I have just done here, or any of the abstract complex solutions. So I try not to do that. Like, I don't know. I'm just warning you. When he says nth root of 2, he may or may not mean the real nth root of 2. And to give an example from what he says right here he says, where the symbol denotes any one of the algebraically indistinguishable abstract solutions in general. I would instead say that the minimal polynomial for zeta, any one of these, pick one, all right, over the rationals of x is equal to x to the n minus 2. That is irreducible by Eisenstein, all right, p equal to 2. That's true for the garden variety nth root of 2, but it's also true for the nth root of 2 times your favorite root power of a root of unity of n. All right. Anyway, that says that the degree of the extension of Q by zeta, my zetas are degenerating a disease. My zetas have a disease. Sorry, that's kind of horrible. But no more than usual. Anyway, this is a degree n extension over the rationals, right? Okay. In contrast, what would happen if we let, okay, so, so, so here's the funny thing, right? What's the, can you tell me how, describe this? That could be different. But what are the two choices? There are only two choices. It's either R or it's what? R would be, if zeta was what? If zeta is real, it's already in the real numbers, right? Right? If it's complex, right? Then I'm telling you that that will force the extension to be the complex numbers. How do I know that? Well, if zeta is complex, that means it's equal to something like the nth root of 2, right, times e to the what? Something like 2 pi over n to some power, right? Let's say it's the jth power. And so if you look at that, what's going on here is you've got the zeta is the nth root of 2, right? The ordinary real nth root of 2 times what? Times something like cosine of 2 pi j over n plus I times the sine of 2 pi j over n. But the thing is, if you extend by zeta, you're extending to a field, right? Which means, what are the rules of R parentheses zeta is the field generated by zeta. It is the smallest field, which contains both the real field and this new element zeta, right? Now, the universe in which we're playing is complex numbers, right? Because zeta is a complex number. So if you look at this, see, how do I know that I is in here? So again, we're also assuming what? This is non-zero, right? So if you look at this expression, what you've got is that zeta over the nth root of 2 minus the cosine of 2 pi j over n, all divided by the sine of 2 pi j over n is equal to what? I. Right. But these things are in R adjoint zeta, because we're doing nothing more than dividing in R adjoint zeta. We're subtracting a real quantity, which is in R adjoint zeta, and we're dividing by a non-zero real quantity, which is also in R adjoint zeta. And a field is closed under addition, subtraction, and division, right? So if you can form some expression like this, that this is, again, in R adjoint zeta, which means that I is an element of R adjoint zeta, but what's that say? If you take R and adjoin I, you get the complex numbers. So that's how I knew that the extension either goes to R or C here. Yeah.
This is all, like, starting with the top zeta right there, you're saying that if it's not real, right? Like,
Yeah,
the
zeta
imaginary thing.
genuinely complex, right? And so this calculation breaks down if it's real, because I can't do this. That's 0. So I can't do this calculation. I does not meaningfully, I mean, it's not there. His third example here, actually his fifth example, he has p of x equal to x cubed minus 3x minus 1 over q. All right. He claims this is irreducible over q. All right. And he says you can argue that by the rational roots theorem. All right. Because if you look at it, you can prove that the graph only has one real 0, and it's somewhere between, it's alpha, the one real 0 is somewhere between 0 and 2. And if you check the rational roots for this polynomial, none of them are between 0 and 2, so it's irreducible. This is the argument that can be given. So anyway, you can prove that this is irreducible. Consequently, if we look at, so let p of alpha equals to 0, then m alpha q of x is this guy, all right? And so this would give us a degree 3 extension over the rationals, which is a little bit, I mean, of course, we could also do what? If you want a different degree 3 extension over the rationals, what could you do? Would be easier. Yeah, if you just want to give me a degree 3 extension over the rationals, the cube root of 2 would be an easier example. So the reason for this example, it shows up as we go on. All right, it's something he comes back to as you go on. All right, move along here. Proposition, come on. Prop 12, he says, an element alpha is algebraic over f if and only if the simple extension f of alpha over f is finite. Let's try that again. Alpha algebraic over f if and only if what? If and only f adjoint alpha over f is finite. He says, more precisely, if alpha is an element of an extension of degree n over f, then alpha satisfies a polynomial of degree at most n over f. And if alpha satisfies a polynomial of degree n over f, then the degree of f alpha is at most n. So let's try to work through this, all right? Proof. So let's suppose alpha algebraic over f. What is it?
The thing that you just read, did that have anything to do with this, or is that like a completely different?
It's the rest of this proposition.
Oh.
It says that anyway. So suppose alpha is algebraic over f. What's that mean?
There's a polynomial, minimal polynomial that
Uh-huh.
is equal to 0 under when you plug in alpha.
Right. And what else? F adjoint alpha is what? Isomorphic to, how's it go? Oh, my F all of a sudden got a double bar. Oops. My fields are showing.
F of polynomials
Yeah.
over
Yeah, polynomials are x. And I'll give you a Langle. And I'll give you a wrangle. There you go, right? But what? What's the degree of alpha? Right. Which is, of course, less than infinity, right? I mean, it's a polynomial. So it's a finite extension. All right, well, that seemed almost too easy, right? How about the other direction? So what's our starting point? Assume that f adjoint alpha is over f is finite, meaning that f adjoint alpha over f has degree n, right? But 1 alpha, alpha squared, alpha cubed, alpha n is n plus 1 vectors, right? Is linearly dependent in f alpha by assumption, right? By assumption star, that says that we can have at most n linearly independent things, right? Because it's a vector space of dimension n over f. So if you look at 1 alpha, alpha squared, alpha to the n, there must be what? There exist, C1, I'll tell you, C0, C1, Cn in f, right? Not in f, in f. Good grief, not all 0, such that what? If we look at f of x equal to C0 plus C1x plus plus Cnx to the n, we have what? F of alpha right? I mean, we can construct, there's this non-trivial linear dependence. We use it to build the polynomial, which takes alpha as a 0. I think I said those things out of order, but I mean, my writing is kind of out of order, right? I should start, I'm sorry, guys. This comes first, and then this comes second. There's no f of alpha here. This, therefore, 0.3 f of alpha equals to 0. Good grief. I'll go back to my ball. Seems like there's some joke to make about this. What is it? I am on camera. Some joke. I don't know what it is. Anyway. If only I could think of one. Sorry. And what does that say? That says that alpha is what? Therefore, f is algebraic, right? Alpha is algebraic. Now, the other sentence that I read but didn't write down said that there must exist a polynomial, right? So, alpha algebraic over f. let's see here. Well, I mean, this is good what we've done. Let me not ruin it. I'll read the sentence again. He says, more precisely, if alpha is an element of an extension of degree n over f. Okay, so the second sentence is a slightly logically different thing. All right, so like, let me separate out the second sentence as a standalone proposition. So let's call this proposition 12b, because it's actually important. It's actually really important, believe it or not, for the rest of the semester. Weirdly enough, this is actually a kind of really critical calculation, strangely enough. So proposition, I don't think I'm exaggerating that much. 11b. What's that? Oh, 12. That's okay. At least I have until. Hey, come back here. Come back. Sit. Still got like 30 minutes, right? Let's see here. So. 12. Let's see here. Proposition 12b. Alpha, an element of an extension of degree n, if alpha is an element of E over F, where E over F equals to n, then alpha satisfies f of alpha equals to 0, where the degree of f of x is at most n. It says, and if alpha satisfies a polynomial of degree n over f, then the degree of f alpha over f is at most n. Let's say if the degree of f of x is equal to, let's say, m, and f of alpha equals to m, good grief, 0, then f adjoin alpha over f, all right, is less than or equal to m. Notice that we're not assuming f is the minimal polynomial here.
So for the first part, are you assuming that there is some, like, that there is a polynomial where it's equal to f? Like, you're already assuming that it's algebraic in that?
Then there exists f of x in such that. I think we've actually already proved these things. If you look at the proof, we already did, but you have to kind of think through it. Like, all right, so suppose it's a finite extension, right? And alpha is an element of the extension. Because the extension has degree n, that means that 1 alpha, alpha squared, all the way to alpha to the n is a linearly dependent set. So there exists a non-trivial linear combination, like I said over there. And so we can construct the corresponding polynomial, which takes alpha as a 0, right? That's still true outside, this claim right here, this logic is still true independent of f alpha being the extension field. Like as long as the extension field E here has degree n, this logic holds, right? It's not because it's f alpha, that's just coincidental to this proof, the if and only if proof. In fact, I really would rather that this proposition were stated part A, part B, and then part C being the if and only if. Right? If I had more time and common sense, I would have reformulated the proposition 12 as like part A, part B, and then like the first sentence would be part C, because it's really using both of these things together. This here okay, so if the degree of f of x is m, and f takes alpha as a 0, that means that the extension by alpha can't be larger than degree m. Why is that? Because we know that the minimal polynomial must divide a polynomial which takes alpha to 0, right? So what's that mean?
Well, the f alpha, f adjoint alpha over f is equal to the degree of the minimal polynomial.
Right,
Which means
exactly.
it has to be less than the degree of anything.
So that has to be less than or equal to the degree of a polynomial which, yeah. So I will try to refer to these as proposition 12b and proposition 12c for future reference, just, to be. All right. Corollary 13, if extension k over f is finite, then it is algebraic. Let's look at his proof. He says if alpha is in K, then the subfield f of alpha is a particular subspace of the vector space K, right? Hence, and this is just like subspace logic, right? If we look at the dimension of a vector space, a subspace, what's the dimension? Dimension of a subspace is smaller than what? The dimension of the vector space in which it sits, right? So this is the subspace dimension, and this is the dimension of K over F, right? So if F adjoint alpha is a subspace of K, then it must be the degree of F alpha over F is less than that. But what did we say? Oh, remember we're assuming what? That the extension K over F is finite, right? So this is less than infinity. And this is less than that. So what does that say? That says alpha is algebraic, right? Going back to proposition 12. Remember alpha algebraic if and only if we just verified that the degree of f alpha over f is finite. It follows then that alpha is algebraic over f. But which alpha is this true for? Right, we just an arbitrary one, so there you go. It's an algebraic extension. All right. Now his next example is quite powerful. It's quite powerful. And his next example simply says that any extension of K, any extension K of F of degree 2 is of the form K equal to F adjoin the square root of D. Where D is an element. D is an element of F which is not a square. In other words, there does not exist, right? What does it mean to be not a square in F? That means that there does not exist, like beta in F such that what? Right, beta squared. This terminology we use in number theory a lot, right? Talking about a square, something being a square. Now this assumes that the characteristic of the field is not 2, all right? Maybe we'll come back and prove this another day. I just wanted to state this for you at the moment. Then Theorem 14, I should probably take like 10 minutes to kind of carefully go through that because we keep using that. A lot of the examples that we look at end up being degree 2 extensions, so knowing that any degree 2 extension can be looked at as adjoining a square root, that's a very useful thing to know in like examples that follow from here on out. Theorem 14 I proved last class, which is that the if we have an extension by an extension, the degree of the extended extension is the product of the degrees of the extensions. And then corollary 15. Corollary 15. But what we haven't done yet is use that. So let me show you what I mean by that. So let me lead with a question. Do there exist A, B, C in the rationals, all right, such that A plus B alpha plus C alpha squared equals the square root of 2, given alpha cubed minus 3 alpha minus 1 equal to 0? I think that's a kind of intimidating question, right? Let's see how to solve it. Check this out. So here's the logic. Square root of 2 is not an element of Q adjoin alpha, where the minimal, where alpha is real root of x cubed minus 3x minus 1 equal to 0, okay? How can you, square root of 2 is not rational, right? Also, let me just trace out the logic here. Q adjoin the square root of 2 over Q is equal to 2. Q adjoin alpha over Q is equal to 3. All right, so great. We need corollary 15, which I haven't written yet. Corollary 15, what's it say? L over F, finite extension, and K subfield of L containing F. In other words, F fits inside K, fits inside L, then the K over F must divide L over F. So this is an immediate consequence of the thing I proved at the end of last class, all right? So let me try to draw a picture here. So we've got Q adjoint alpha up here, right? We've got Q down here. We're trying to stick, in some sense, we're trying to stick Q adjoint square root of 2 on here, in the sense that we're trying to like look at this as being the, here's the L, here's the possible K, here's the base field F. We cannot have Q adjoint square root of 2 as a subfield of Q adjoint alpha. This is not, no. 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 Why? Because Q adjoint root 2 is degree 2, and Q adjoint alpha is degree 3. We can't have a degree 2 subfield of a degree 3 extension. That's corollary 15. And you understand, if the square root of 2 was in Q alpha, right? What does that mean? Do you understand why this is relevant? If this is true, then what? That means that Q adjoint the square root of 2 is a subset of Q adjoint alpha. If root 2 is in there, then Q adjoint root 2 is in there, which would say that Q adjoint root 2 is a subfield of Q adjoint alpha. We would have a degree 2 subfield of a degree 3 over Q extension. That would contradict corollary 15. Why is that relevant to my original question? Because that's exactly what the question asks. Is the square root of 2 in the extension by alpha? Things in the extension by alpha are of the form rational combinations of 1 alpha and alpha squared. So this multiplying degrees thing, it's more than just a fun exercise in linear algebra. It actually allows you to subvert rather difficult calculations when you put your information together correctly. We're going to make this kind of argument more than one time in the future. I mean, this kind of thing we keep coming back to. This is that next idea about, I mean, this is also going to allow us to prove irreducibility in a new way. All right, that's coming up. So, oh, I'm sorry, I seem to be over, but yeah.
I could just be totally missing this, but why the square root of 2 not being, like, why can we say that the square root of 2 is not in Q adjoint alpha?
Because if it was, if square root of 2 was in here, I mean, this whole thing is proving that. If it was in there, then Q adjoint root 2 would be a subfield of that, right, which would mean we'd have this tower of field.
That is not, okay, so you set those things up and then
to prove that.
Corollary 15 to explain all of it.
Yes.
Okay, gotcha. That was my question.
And then how does that answer the original question? Can you say that one more time?
Because solving this equation is tantamount to answering the question, is square root of 2 in Q adjoint alpha? Because Q adjoint alpha is a degree 3 extension over the rationals, which has basis 1 alpha alpha squared. Yeah, yeah. I love this stuff.
Can I turn it off?
Yeah, you can turn it off.